Hello everyone, and welcome to today's chem lesson. Today we're going to introduce the idea of Lewis structures, which is a way of writing or drawing, however you want to look at it, the atom and keeping track of its valence electrons. Now, last time we said that the valence electrons are going to determine a huge amount of the properties of an atom, right? The huge amount of properties of an element. And so it's important that we keep track of how many valence electrons there are. And it gets a little bit cumbersome to draw the shell model for especially some of the bigger atoms. We don't want to have to draw this every time. These inner atoms, or these inner electrons, don't really matter to us. We care mostly about the valence, and so we want something that can identify the element and how many valence electrons it has. And that's where a Lewis structure comes in. A Lewis structure is based around the symbol of your element. Right? We take our elemental symbol, whatever it happens to be. I'm going to put an X here. Right? If I'm doing carbon, that's going to be a C. If I'm doing oxygen, it's going to be an O. If I'm doing iron, it'll be Fe. Right? There's whatever your elemental symbol is in the middle. And what you're going to do is you are going to put dots around the symbol to help represent how many valence electrons it has. And we have to do this in a very specific way. You must put 2 dots on either side of the symbol in order to show up to 8 valence electrons. And on top of having 2 on each side, we have to put them there in a very specific order. The first 2 need to go up top. Then we need to go around in a clockwise fashion. So the third one's going to go here, 4th on the bottom, 5th on the left. And we're going to keep going around. So our 6th is also on the right side, our 7th is on the bottom, and our 8th is on the left. It does not matter what position you put the dots in. Right, for example, if I have something with 3 valence electrons, the first 2 electrons are going to go up top. The third electron can go pretty much anywhere along this side. No one is going to nitpick you for putting it here or drawing this picture and putting it here, or drawing this picture and putting it there. All 3 of these are the same picture. Now, if you were to draw a Lewis structure of something with 3 valence electrons and put the dot on the bottom, that is wrong. We must have the first 2 up top, the third on the right, 4th, 5th, 6th, 7th, 8th, kind of circling around to fill in those spots. And the reasoning for this very specific order is because of the quantum mechanical model and the way that our orbitals work. We don't need to know the why in huge detail, just knowing that it is important that you put these dots in the right spots. All right, put the dots in the right spots. There's a rhyme for you. And as we continue in this unit, we're going to see how these valence electrons and how these dots placed around really make a difference and really impact the properties of our elements. Now, we're going to do a little bit of practice right now. And the practice that we're going to do is drawing the Lewis dot structures of the first 18 elements. I'm going to put this up here to remind us of the correct way to place our electrons. Right, first and second, third, fourth, fifth, sixth, seventh, eighth. And using your periodic table, look at how many valence electrons each of these things has, and draw the correct Lewis dot structure. Put these dots around these symbols to get the correct configuration, to get the correct Lewis structure. I'm going to give you about 3 minutes here. When we do these correctly, we're going to end up with some diagrams that look a lot like this. And before I turn to the slide that shows the answers, if you need more time, please pause the video and keep working. But the correct answers here should look like this. We will have our dots placed around correctly place the first two up top, the third and the sixth on the right, 4 and 7 on the bottom, and 5 and 8 on the left. Hydrogen has one valence electron, so its one valence electron gets put up top. Helium has 2, so both go up top. Lithium with 1, beryllium with 2, boron with 3, carbon with 4, nitrogen with 5, oxygen 6, fluorine 7, neon 8, and then we go again 1 to 8 over here in our third row. Now, there are a couple of things that we notice. There are a couple of patterns that pop up as we look at just these 18. Right? If we looked at the expanded periodic table and kept drawing these, we would see these patterns expanded. But you don't need to. You don't need to draw them all to see it. If you look at a column, you'll notice that the elements in the column have the same number of valence electrons. Right, the first column has 1 valence electron. The second column has 2 valence electrons. Third here has 3 valence electrons. 5 valence electrons. 7 valence electrons. And we see that pattern as we look up and down. Another pattern that we see is that as we move from left to right, we increase the number of valence electrons by 1, right? 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8. And once we hit 8, we start again. 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8. So as we go from left to right, we are filling up the valence shell. There's one glaring exception to this pattern, though. There's one person who refuses to fit in, and that's helium. What makes helium so special? Why does helium hang out over here on the far right side of the table when it has a perfect spot for it right here? Right? Helium could very easily hang out right here and fit in perfectly with beryllium and magnesium. Right? Why? Why isn't helium here on the left? Why does it belong here on the right? It's not because of the fact that helium is a gas. It's because of the fact that helium only has one shell. Think back to when we first talked about the shell model. We talked about how many electrons fit in each shell. First shell holds 2, second shell holds 8, 18, and the rest hold 32. Right? This is the last pattern that we see. Each row refers to a specific shell. The first row has the valence shell. The outermost shell is the first shell. The second shell, or second row, starts to fill up the second shell. The third row starts to fill up the third shell. Fourth, fifth, sixth, seventh, as we go down, each row represents a new shell being added to the atom. And so if we specifically focus in on helium, helium has filled its shell. It has 2 out of 2 electrons. These two, beryllium and magnesium, have 2 of 8. Helium doesn't really fit here because it doesn't match the rest. It has 2 of 2, not 2 of 8. It's got a full shell, so it should hang out over here with the other elements that have full shells. so once again, we get a couple of patterns that show up. Alright, let's make some bullet points to capture these patterns. First, elements in a column. Alright, so looking up and down. Share the number of valence electrons. Right? Fluorine and chlorine both have 7. If you look down below them, iodine and bromine both have 7. Right? Everything in this column has 7 valence electrons. Everything in the first column here has 1 valence electron, even as you look down. You go down to francium in the 7th row. Second pattern, moving left to right. Fills up the valence electrons. As we move, starting from the left and then move all the way to the right, we go 1, 2, 3, 4, 5, 6, 7, 8. We fill up that valence shell. And the third pattern, the third thing we notice here, is each row matches up with the valence shell. So the first row has the first shell as the valence. The second row has the second shell as the valence. The third row has the third shell as the valence. I'm going to keep going. Fifth row represents the fifth shell. The sixth row represents the sixth shell. And because of these patterns, because we can say that lithium has the same number of valence electrons as hydrogen, but has one additional shell, right? 2 shells versus 1 shell. Because we can look across the row and say, okay, there's fewer valence electrons on the left, more valence electrons on the right. Because we can look at these patterns, we can actually make trends. We can look at things that are true for the whole periodic table as we look at it in the macro sense, as we look at it as an entire completed thing. And what we're going to be doing for the next couple of videos is looking at these periodic trends. These properties that we can learn a bunch about without having to dive deep into an individual element, but instead by looking at the patterns across the whole table. We're going to jump into that next time, but for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.